Good morning, fellow mathematicians. Welcome back at Papa Flammy's Polygamma X course. So we are going to derive a little integral representation for our Polygamma function right here. And just like with the Digamma function and many other special functions, there are so many integral representations out there. Contour integral representations or simple integral representations, just like the one we are going to derive today. So many possibilities and so less time on our hand, not so much time on our hands. So yeah, let's go ahead and get started. So at first I want you guys to observe something. Either we take a look at this thing right here, we can do this, or we are going to take a look at this thing right here, okay? I've derived this little expression for the Polygamma function, so getting rid of this negative 1 over z term, because actually deriving the integral representation is way easier using this form right here. I want you guys to notice that this thing right here is nothing but, well, if we do a little integral thing right here, this is basically nothing but x to the nth power over n evaluated from 0 to 1. Okay, I hope you agree with me that this is true. Minus, and you might have guessed it, x to the n minus 1 plus z power over n minus 1 plus z from 0 to 1. And yeah, this is so easy to see. So this is going to be quite a short video actually. So you see, how can we arrive at those x to the something values? Well, we just have to integrate them in a certain way. So this is nothing but negative gamma plus an infinite sum running from n equals to 1 to infinity of, and this is nothing but an integral from 0 to 1. So on the one hand, we are going to integrate x to the n minus 1th power, because we are going to raise the power by 1 integrating polynomials, and well, this is going to arrive at n in this case. And here you basically just want to subtract 1 from this thing. So this is going to give us negative x to the n minus 1 plus z minus 1th power, but this is nothing but n minus 2 plus z power. Okay, integrated with respect to x. And we already came pretty far with this little observation. If you are fucking better, you can actually bring this stuff to the inside, okay, right here. So bringing this infinite summation to the inside. Integrand strictly positive if you break those up into two separate integrals using the linearity of the integral. I'm terribly sorry. So yeah, you might actually be able to Fubini this shit right here. So without any restrictions, let's just bring this infinite sum to the inside, and let's also break this infinite sum up into the sum of this thing minus the sum of this thing. Okay, we are going to get negative Euler-Mascheroni constant plus an integral running from 0 to 1. On the one hand, we have the infinite sum running from n equals to 1 to infinity of x to the n minus 1th power. Okay, this is our first boy right here, our first infinity boy, and negative this infinity boy, this very infinity boy, of x to the n minus 2 plus z power, integrated with respect to x. We're just going to take a look at this thing right here, because it's kind of obsolete doing the same thing for this once again. So yeah, we're just going to take a look at this, and deriving this is analogously the same. So taking a look at this infinity boy, from n equals to 1 to infinity of x to the n minus 1th power. I want you guys to notice that this is nothing but x to the nth power times 1 over x. So let's bring the 1 over x to the outside. Okay, that's something we can do. And I'm going to put big parentheses here. Times the sum running from n equals to 1 to infinity of x to the nth power. And yeah, here's where another bit of magic is going to happen. You see, we have kind of the geometric series right here. So all that's really missing is our 0th term, okay? But if we plug 0 into here, x to the 0th power is just 1. So we are doing the same algebraic manipulation as most of the time. We've already done this plenty of times. So adding 1 and subtracting 1 right again is like adding 0 and adding 0 to something is fine in the real numbers. Nothing really changed. If you have an apple and you don't place another apple next to it, then you still end up with this one apple you have. Meaning, overall this right here is going to evaluate to sum running from n equals to 0 to infinity of x to the nth power is nothing but 1 over and this is 1 minus x. Okay, geometric series, easy stuff. And you see, it does work out because our integral runs from 0 to 1, so it's still in our radius of convergence. So everything is Gucci at this point. Then we have this negative 1. Okay, we want to bring it to the same denominator right here, so we have to advance negative 1 by 1 minus x over 1 minus x, leaving us with 1 over x times. Okay, putting the negative sign into here turns around to x minus 1 over 1 minus x plus 1 over 1 minus x. Overall, positive 1 and negative 1 are going to cancel out. Then we have nothing but x over 1 minus x. 1 over x and this x are going to cancel out in the process, leaving us with 1 over 1 minus x. And this is kind of cool, it's just our regular old geometric series that we have here. I just like doing those algebraic manipulations so that you can actually see where this stuff comes from. We can go, like I said, through the same process on this thing right here like we did here. The only difference is that we have to break this up. So if we take a look at x to the n minus 2 plus z to the power, this is nothing but, okay, we can break out the 1 of the x to the negative ones. Okay, so we are going to get 1 over x, and then we have x to the nth power. So putting this into the geometric series, but we also have x to the z minus 1th power left. Okay, all this really different in the process we are going to get is that we have x to the z minus 1th power over 1 minus x. So that's all that's really going to be different. So overall, our Polygamma function that we cherish and love can be expressed as nothing but, okay, we have negative gamma, as always, Euler-Mascheroni constant, and then we have plus an integral from 0 to 1 of, what are we actually going to get? Okay, putting this into our geometric series stuff, it's going to give us 1 over 1 minus x, and then plus, no, it's going to be negative because we had a negative sign right here, I'm terribly sorry, x to the z minus 1th power over 1 minus x. Putting those on the same denominator, we actually can finish our work up with this very expression. Whew. And voila, my boys and girls, this is our integral representation of, our Euler-Mascheroni. No, not Euler-Mascheroni constant, our Polygamma function. I was thinking one step ahead because, like I said in the beginning, there are many integral representations of special functions like those. And you can easily I really didn't figure it out up until now, but it's probably not too hard to write your Euler-Mascheroni constant as this integral representation we have had in our Putnam video thing, and then you can actually bring those two together in some way and derive yet another integral representation. So that's something you can probably do. If I get around figuring it out, then I'll let you know with a little video. But up until then, I thank you guys for watching. If you did enjoy this video, please like, subscribe and recommend the channel if you like. If you want to support the channel a bit more by those fundamental theorem of engineering shirts I created, they are great. Obviously, it has to do with mocking engineers, so that's always great. And yeah, you can also support the channel on Patreon. Don't forget to visit the second channel and the website and the subreddit and Twitter and Facebook and oh my goodness, so much stuff to handle at one time. No matter what you do, thank you guys for watching, and until the next video, have a flammable day. See ya!